Do you remember what happened back in spring 2020?
COVID-19 is spreading across the world. People start working from home, borders close, masks become the new reality, and anything that draws a crowd shuts down, sport included. Dozens of football leagues were stopped before they could finish, which left one big question: what do you do now? How do you decide the winner? And every country answered it differently. Some leagues carried on behind closed doors. Germany, Spain, Italy. The Premier League resumed later that summer, giving Liverpool the first league title in 30 years. Belgium just handed the trophy to whoever was top when it all stopped. The Netherlands cancelled the season entirely, naming no champion at all for the first time in the league's history. But the strangest stories came from France and Scotland. In League One, the league rearranged the table by ranking the clubs on points per game. As a result, one club lost its place in Europe and the bottom two were relegated. Scotland did exactly the same. In both countries, the relegated clubs took it to court, though the decision stood.
The irony is that mathematically, every league that ended its season early got the answer wrong. But how do you divide the stakes in an unfinished game? That's exactly the question that was asked in France almost 400 years ago, and it changed everything. It gave birth to probability theory, which sits at the heart of the modern world, including AI, the internet, financial markets, your favorite recommendations, and lots of other things. Yet this simple question has confused many brilliant people. But why does this question have so many different answers? How did it launch a whole new branch of mathematics? What is the right answer? And what should League One have done differently in 2020? This is Vital Math. Here we explore and enjoy the beauty of mathematics. The problem of points. Let's go! Let's start with the problem itself.
Imagine two players with equal skills and luck. They put 64 gold coins on the table and agree on a simple rule. The first to reach 6 points takes everything. The game itself doesn't matter. It could be flipping a coin, rolling a die, or a card game. So they play on, and then suddenly, with the score at 5-3, the game stops. Maybe a quarrel breaks out, maybe the town watch arrives to shut down the gambling, maybe one player is called on a duel and never comes back. So the question is, how do you divide the pot fairly?
How should you even think about that? It always gets interesting when we try to translate fairness into mathematics. That's where people start to argue.
One may suggest giving everything to the leader. Why not? That's similar to what Belgium did. One may say it's fair to split it 50-50, 1-1. Forget the score, nobody actually won, so give everyone their stake back. That's similar to the Netherlands approach. One may say divide it in proportion to the score, 5-3. Others argue you should divide it in proportion to the points each player still needs, 3-1. Or someone reasons their way to 2-1. Look, the first player is 2 points ahead in a game to 6, that's 1/3 of the way to victory. So give 1/3 of the pot to the leader outright, and then split the remaining 2/3 evenly. The leader ends up with 1/3 plus 1/3, that is 2/3 of the pot. Or in other words, the pot should be split in proportion 2-1.
But from a probability standpoint, every one of those answers is wrong. The real answer is 7-1. Let's step into the matrix for a moment and watch how the future could play out.
Let's take this 5-3 position and finish the game thousands of times. This chart shows how often the first player ends up winning, and as we run it more and more and more, it closes in on about 88%. That is 7-1.
But why that proportion? Well, it took humanity a few hundred years to find out.
Humans have always dealt with chance. Long before dice, they were straggly, the little ankle bones of sheep that when you toss them can land on 1 or 4 uneven faces. 6-sided dice appeared in Mesopotamia more than 5,000 years ago. Later, the Romans gambled on them obsessively.
For thousands of years, no one saw chance as something you could measure. The roll of a die was the verdict of fate or the will of the gods, but that began to shift when Europe fell in love with gambling.
Playing cards reached Europe in the 1300s and spread so fast that cities started to ban them. The city of Bern ruled cards illegal in 1367, but it didn't help, and eventually the games drew the attention of mathematicians. The unfinished game was among the first puzzles to attract those math thinkers. The first manuscripts with the problem date back to around the 14th century. But the first who brought the problem to broad attention was Italian mathematician Luca Pacioli. In 1494 he wrote a giant mathematics textbook called the Summa, with both the problem and a solution. His solution was simple: divide the pot in proportion to the points already won, 5 to 3 in our case. Half a century later, Girolamo Cardano, the first to reckon with imaginary numbers, criticized Pacioli. Cardano argued the answer had to depend on points remaining. His answer in our case would be 3 to 1. The 17th century brought a fresh wave of gambling fever. In Venice, the world's first government-licensed gambling house, the Ridotta, opened its doors in 1638. And in Paris, aristocrats spent days and nights in the salons and private mansions. Among them was Antoine Gombeau, who called himself the Chevalier de Marais. He was no real nobleman, the title was his own invention. He was a writer, a wit, and a relentless gambler with a sharp instinct for dice. At one of those Parisian salons, he shared his betting puzzles with his friend, a young mathematical prodigy, Blaise Pascal.
Pascal was hooked. By age 30, Pascal had already proved the celebrated geometry theorem about a hexagon inscribed in an ellipse, resolved one of the greatest debates of his age, the existence of the vacuum, and built one of the first mechanical calculators. But this simple-looking gambling problem became a real challenge. So in the summer of 1654, he wrote to one of the best mathematicians in France at that time, Pierre de Fermat. Look at these letters.
Pascal writes first, asking about the first puzzle, but that opening letter is lost. Fermat replies with the solution, Pascal writes back, now with the unfinished game puzzle. Fermat answers with a message of his own. Pascal pushes back, convinced Fermat has misunderstood. Even though reading it now it looks like Pascal was the one who struggled to get it. Fermat patiently explains, and by autumn Pascal agrees. The methods are different, but the result is the same. They are both right. The harmony is restored.
This exchange of letters in the summer of 1654 made a quiet revolution that changed the world. But what exactly did Pascal and Fermat propose? Pascal's approach was a little more sophisticated, built on recursion, but Fermat found an elegant and simple solution. His idea was stop looking at the past and look instead at every possible future. Look at how it works.
The score is 5-3. The leader needs just one more point. The other player needs 3. So the game would be decided in at most 3 rounds. Now imagine always playing all 3, even when someone would have already reached 6 points. There are 8 equally likely scenarios. Go through them and ask, in how many does the second player win? Only one, the single sequence where he takes all 3 rounds in a row. In the other 7, the leader reaches his point and wins. That's why the answer is 7-1. That is the real fair answer.
Pascal reached the very same answer from the other direction. He worked backward. He figured out the value of each next point, then folded it step by step into the score before it. That method ties directly into his famous triangle. So the problem was solved, and to be honest, it looks like a simple school puzzle. But why was it so impactful? The exchange between Fermat and Pascal is widely regarded as the founding moment of mathematical probability. For the first time in history, chance turned from fate and fortune into something you could compute. That might sound modest, but it was a huge mental revolution. Imagine, for thousands of years, mathematics has been used to measure geometric shapes and other things you could see. But now you could point it at the future. Of course, you still don't know what will happen, but at least you have an instrument that gives you some grip on it. And the beauty of this unfinished game puzzle is not only in probability. The real genius of Fermat and Pascal was in a shift in the question itself. Not how likely is it, but what can you expect? They invented a new concept, expectation. Their answer divided the stakes in proportion to each player's expectation of winning. That was the first notion of mathematical expectation, the probability-weighted value of an uncertain future. And that notion became the foundation of probability theory.
A few years later, the Dutch scientist Christian Huygens took these scattered ideas and gave them a spine. In 1657, he wrote the first printed treatise on probability, with expectation as its central, powerful concept. He even gave the first mathematical formula for it, with p chances at A and q chances at B. The expected value is given by this nice little formula.
You can't control what happens next, but you don't have to be blind to it either. That's how uncertainty became something you could reason about. Today, that idea runs underneath almost everything. The weather forecast, the price of your insurance, risk management and banks, trading on financial markets, the reading of a medical test, every recommendation for what to buy or watch next. Probability and expectation sit at the very heart of AI as well. And all of it started with a simple question: how to split a pot in a game that never got to finish. But let's get back to the question we started with. What should League One have done differently in 2020? Mathematicians got interested in this question too. It's a little more complicated than a coin flip game, of course, since teams differ in strengths and there are multiple factors affecting the result, but they did essentially what Fermat suggested: simulate the future. One of the approaches used the bivariate Poisson model to play out the unplayed fixtures thousands of times. They found that champions usually came out the same, but down at the bottom and around the European places, the probabilities didn't always match the league's official standings. 4 centuries on, and we are still arguing about how to divide the stakes. But let's summarize key takeaways. So what are the 3 things I'd like you to take away from this simple question: how to divide the pot in an unfinished game? First, the question can have many answers if you ignore math. Our intuition about fairness and chance is often wrong. With simple, reasonable-sounding logic, you can arrive at several different answers. And in today's age of AI reasoning models, it makes it even more important. When we rely on reasoning, can it lead us to a fair answer? Second, the unfinished game question led to the birth of probability theory. The division of a pot in an interrupted game gave us mathematical expectation, the seed of a new math discipline that over time grew into insurance, stock markets, risk management, statistical physics, machine learning, and most of modern AI. All of that traces back to this exchange of letters between Fermat and Pascal in the summer of 1654. Finally, this is the question that made us rethink the future. We cannot know exactly what will happen, but we can at least understand what to expect to some extent. We can weigh the possible futures by their probabilities and turn uncertainty from pure fate into mathematics. Fermat, Pascal, and the unfinished game puzzle gave us the first tools for managing the world of ambiguity around us. Although, as history shows, this very notion of expectation was broken less than 60 years after it was invented. But that's a story for another time. Let me know in the comments what you think about the problem of points. Please share this video and subscribe to the channel to see even more stories about the beauty of mathematics. Think and enjoy the beauty of mathematics. See you next time!